So we will now look at divisibility by 3, and again in the same way, usually this is done as a pattern, an extension of a pattern, and we can also look at it logically in terms of the divisions. Yeah? So usually we write down the 3 tables and then we look at 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, and in the meantime we see if we can figure out a pattern. And we say, okay, let's add the digits. So 1 plus 2, so this will again give a 3, and 1 plus 5, this will again give a 6, and so on. So again we notice that there is a repeating pattern, the 3, 6, 9 pattern when you add all the digits. In this case there is only one digit, nothing to add. But when you go further, you continue discovering there is a 3, 6, 9, a 3, 6, 9. So we tell children that okay, all the numbers that are multiples of 3 will always have this pattern of the digits adding and adding to 3, 6 or 9. So this is sort of one way of like mathematical induction, sort of saying, yeah, it's true. So now we'll look at again, let's say a 3-digit number, the same 3-digit number we looked at for divisibility for 2. If we take the number, we have hundreds, we have tens, and we have ones. So as last time, 5 is 5 hundreds, 2 is 2 tens, 4 is 4 ones. So as in last time, let's look at a 10. So if I look at a 10, I have marked it here. We have actually 3 sets of 3s. So you have the first 3, you have the second 3, you have the third 3, which I have marked like this, as you can see. So if I take a 10, once I am done with the 3 3s, I will be left with a single 1. So when I divide, for example, 2 tens, I will be left with 2 ones. So now if I look at 100, now 100 is actually just a combination of tens. So when I combine the tens, I see that there is 1 left, there are 10 ones that are left. And then these 10 ones also is a 10. So basically in the end, there's only 1 left. And if you think about it, we are basically saying 9 is a multiple of 3, 99 is a multiple of 3, 999 is a multiple of 3, 9999 is a multiple of 3. So basically any of the powers of 10 will always have 1 left. So in order to test the divisibility, it's enough to test those ones that are left that we were not able to divide. So when we divide the 100, each 100 will give 1. I should write like this. Right? So basically, depending on number of hundreds, I will have that many ones. 5 ones that I need to deal with. Depending on number of tens, each 10 will result in 1 1. So I will basically have to figure out if this 1 is still divisible by 3, because that's a remainder. And same way when I have the ones, I will have 4 ones. So these are all remainders. After everything has been divided, these are all remainders that are there. So if I check if the remainder is divisible by 3, then the entire number is divisible by 3. So that's basically the idea of dividing by 3. So just one note on a shortcut that's available when you do that is that, let's say you have a large number, right? You have 69,564. So then generally children would add up all the digits. Now that's not necessary, because the number 6, number 9, number 3 are already divisible by 3. So when you are adding the numbers, you can skip all of these. And you can just add 5 plus 4, which is 9. This number is divisible by 3. Okay, so actually extending this to divisibility by 9 is fairly straightforward. Just like we saw, when I have a 10, 9 will have one digit left. Only one will be left, not a digit. One, every 10 will have one left. Same way 99 is also divisible by 9. So there will always be one left out of 100, and 9989 and so on. So basically again all the digits have to be added, and those digits you have to be able to divide them by 9, not by 3 in this case. You have to divide it by 9. Pause. And so that's it. Divisibility by 9 means the sum of the digits need to be divisible by 9. Obviously, if there are 9s in the number, you can drop the 9s in the number. And anytime the addition adds up to like an 18 or 9, you can drop those as well. So that's it.